All right, so this is recording too, and I'm just going to do a clap, so it's easy for me to spot, the sync point. All right. So we have Logisim already downloaded, I think. Let's check. Download. It's already downloaded, and we'll start running. It's actually running already. Okay, let's cancel this one and just look at this one. All right. So I'm just checking the meter just to make sure that it's recording. All right. So a mux is basically a selector. Okay. You have multiple input, one single output, and a selection bit to basically specify how should I dial that switch. And then you have one enable, which basically says, yes, we do want to connect that particular input to the output because it can disengage all the inputs from the output. So those are your options. And if you want to play with a multiplexer, you can just build a very simple circuit with a multiplexer in it. So we'll go ahead and start with a multiplexer, and we'll zoom in a little bit just so that we can see better. And once you pop in a multiplexer, the default one only has two inputs, which means you only need one put to select one of the two inputs. This is the output enable, and this is the actual output.
So that one, and what's the name of the one that's just the one bit to select either? What's the name of that one again?
The selection, this is SEL.
Okay, selection.
Yeah, this is called SEL. If you hover over long enough, I think it does not.
And in this case, it's only one bit wide because we only have those two.
Because we're only selecting one of the two, so this is input 0, this is input 0, this is input 1. Now, if you change the number of select bits to 2, then you now have 4 inputs because you have input 0, 0, input 0, 1, input 1, 0, and input 1, 1. And this is actually now a 2-bit input, not a single-bit input anymore. Are we still doing okay so far with a mouse? Okay. And you can just wire up these things too. Now the other one is data bits. Now the data bit thing is kind of like the way it is right now is we have one physical wire going to each of the input points. So it's only good for switching it's only good for switching from 4 input alternatives to 1 output input.
How does that work now? 4 input alternatives to 1 output bit. We think that exactly.
Yeah. So this is one alternative, 2, 3, 4. So you can select one of the 4 sources and connect it to the actual output. But it's 1 bit only. Now with our processor design, I can't just hook up like a parallel 8 of these things to do an 8-bit switch. But that's going to be take up a lot of space, and a lot of wiring. So that's why instead of using 8 of these things in parallel, I just change the data bits here to 8. So now it becomes 8-bit wide, which means this is now an 8-bit wide input port, and this is also an 8-bit output port. So we kind of do okay so far with each setting needs to the whole thing. Okay. So disable output is selectable because you can basically say if the output is disabled, what should it do? Floating is what we are choosing in the design because we basically say do not drive it. The other option is 0, which means you're driving it low. Now, if you're driving it low, that means the same physical wire, the same physical connection on the motherboard or inside the processor can no longer be driven by someone to a high signal. And we don't want to do that. We want to leave the option for somebody else to specify the signal on that line.
So floating also means it's not grounded, right?
Floating means it's not connected at all to the high or the low rail. So it's
the two open.
Exactly. Both switches are open. You're not connecting it to VCC. You're not connecting it to the ground signal. So it's not. No one is specifying. This component is not. So that somebody else is driving. Yeah. It's kind of like in the class setting. You want to. You guys don't want to all talk at the same time because I cannot interpret when you guys are all talking at the same time. And it's the same way here. If you don't have an output disabled, in the class setting, it means you guys are always making a sound. When you're not talking in any particular way, you just gonna, Tech, I have a question. What is that pin doing in this circuit? Like that. Now imagine all 40-something students doing that at the same time. So I'll be hearing mostly like 30-something people doing, and one person is trying to actually talk over that. Okay, so that's without, a floating output. Now, floating output means you're not saying anything. So when you don't have anything to say, you're quiet, you're silent. So this way, nobody is quote unquote driving the air pressure in the room, and so whoever is talking, I can hear them. Is that kind of okay with the output enable thing? Okay. And this is also optional. If you do not have an output enabled, it is always enabled, and that's not what we want. Okay. So we always want to have the option because we can then say, okay, now turn it on, now turn it off. Okay, are we doing okay so far with a mux? Guys okay? Yep.
And so we have the select input, and the next one tells us whether or not, what's the second one do again? Not that one, yeah, that one, but that one tells us.
This is output enable.
Okay, that's right.
Yeah, this is the one, it's kind of like a clutch with a manual transmission. This is your clutch. So when you have a 0 here, it's like pressing your clutch. Okay. So your transmission is disengaged from the actual drivetrain.
So our input won't go to the output, some other.
Exactly. Yep, exactly. Okay, so any other questions? The most important part to remember about a mux is you have multiple input, some mechanism to select which one, and you have one single output. And then you have one clutch, quote unquote clutch, to basically this one here, to disengage the output completely from the actual selected input. Is that okay? All right. So a decoder, which looks like this, kind of like a reverse mux, right? So let me select like 2 bits here, or 2 bits to select. And with this one, you can see that there are some really kind of subtle differences between a mux and a decoder. They are related, but they're definitely not the same thing. With a decoder, you can see that each one of the output is a blue pin instead of a black pin. That means this has to be a 1-bit only kind of output. A black pin means it is multiple bits. Okay, so when you look at a black quote unquote dot, it means that connection is not, it's just a logical one thing, but inside it can be split up into multiple bits. When you look at a blue pin, or when you look at a blue dot, even this one, or this one, or this one, it means it has to be a single bit. It's on or off. It's just on and off, just one single output wire. Okay? But when you look at this one here, it is a 2-bit thing, because now we have 4 possible outputs. We need 2 bits to specify which one of the outputs to be quote unquote connected. But you don't see any input. In other words, if a decoder is really a reverse of a mux, where is the equivalence of this pin here? There's nothing here. And that's because it is implicitly connected to a 1. Which also means if I want to, a decoder is kind of like a demux. Okay, a demux is a demultiplexer, which is actually truly a reverse of a mux. So if I make this a 2 select bit thing, then it looks like this, which looks exactly like that, right? A decoder is exactly the same thing as a demux, except you connect a 1, a constant, to the input. So this circuit is the same thing as this circuit. It's just, it's easier to draw it like this.
That's just meaning the decoder's always on, or?
No, the input is always specifying a 1.
What does that mean exactly?
It means if you select one of the outputs to connect to the input, you're turning it on. Yeah. It's just a constant. It's always on. Okay, but you still have the same select here. Okay, these are the select pins. These are the same thing. So instead of having multiple inputs and one single output, a demux has multiple outputs and a single input. So it's just the reverse. It is really just the reverse. A decoder is a special case of a debug where the input is always a 1. So it cannot be a 0. It is always a 1. You still have the same control mechanism of this one here, which is the enable. In other words, if enable is a 0, then all of the outputs are not driven, they're all floating. So you still have the critical clutch to disengage the input from all of the outputs. So all the outputs will remain floating. Then somebody else can be either driving the line or no one is driving the line.
And that's because we wouldn't, with the select bits, one of them would have to be selected. That's why we have to have that deselect on. Because that's why we have to have the deselect on, because one of the outputs has to be
connected to the one. But if I'm not ready to update any one of the 4 registers, I don't want any one of them to be selected. So that's why I need to have the enable pin to turn off and say, okay, none of you should pay attention because I'm not changing any one of the 4 registers. Is that okay? I mean, it's the explanation of a decoder, which is a special case of a debug, okay? And the way you remember a buffer versus a debug is they're just reversed of each other. One has 4 multiple inputs, 1 single output. The other one has 1 single input and multiple outputs. That's all. And the mechanism allows you to switch, okay, which input to connect to the output, or which output to connect to the input. And you can also disengage and say, okay, let's not drive the output at all. Okay, is that okay? All right. So if this is okay, then we move on to a register, which is kind of like a small, tiny little memory module. And the one that we use is a D flip-flop. It's a funky name, but it's basically a register. It is the one that we are using. No, we're using a register. Take it back. We are using a particular register. So a register has 1, 2, 3, 4, 5. It has 5 interfaces. This is the input. If you want to change, okay, first of all, a register is a memory device. In other words, it is capable of holding its own content, a certain bit pattern. Now, how wide of a bit pattern are we talking about? It depends on how you want to configure it. So in this particular case, I configure my register to be an 8-bit register. So that means it can hold the content of 8 individual bits, quote unquote, indefinitely. Okay. If you want to change the input, or if you want to change the content of a register, then you first present the bit pattern to the input, which is called the data port. So you specify, like 00, 10, 1111, whatever you want to specify to the data port, but it's not paying attention because the enable pin, which is this pin here, needs to be a 1 in order for the register to pay any attention to the D port or the clock line, which is the wedge thing.
So if we were to look inside with the data port hook into the enable pin and the past that would be an open or close switch?
You can kind of imagine like that. Yep. The enable pin is this one. This is the clock pin. Now the clock pin is useful because when the clock has a transition from low to high or from 0 to 1, that is the signal. It's waving a signal to the register and saying, update now. Copy whatever bit pattern is at the D port to your internal content.
Only if the enable pin is on.
Only when the enable pin is on and the clock is having a 0 to 1 transition. A 1 to 0 transition is not useful. It doesn't do anything in the 1 to a falling edge transition.
Would you be able to make the computer more efficient if you can manipulate the other transition?
Not really, because the whole point of a clock in a processor is to synchronize the operation of all the different components. And typically, what you do with a register is when you update it, you kind of leave a little bit of time for the register to quote unquote settle down. And once a register settles down, the output will reflect the actual content. And the output is always reflecting the content.
What do you mean settle down?
There's a delay.
Between it copying the data?
Between the rising edge and the Q port actually reflecting the new content of the register.
And the rising edge is in regards to the clock, right?
The rising edge refers to the clock. So when the clock has a rising edge, it will start the update operation. But it takes a little bit of time for the update to finish and for the output for the Q port to actually reflect the current content of the register.
And Q port stands for what?
That's the output.
Okay. Which is why it's called Q. So it's just
The way it's called Q has to do with a flip-flop, like a D flip-flop, because a register is basically a multi-bit D flip-flop,
okay.
which operates basically the same way, but it's a 1-bit register, and this is a 8-bit register. But I don't know exactly why they call it the Q, why they label it Q, but that's generally speaking, that's the output of a register.
Well, any questions about what a register is and how to make use of a register? The other blue pin?
That's the reset.
So I just send it back to the other.
Yeah, or clear.
They call it clear, but in most nomenclature, when you design a circuit board or when you look at the data sheet of a chip, they usually call this the reset pin because that's how you hook up everything to what we call the reset pin.
Why have that instead of just data that's all zeros go into it to reset it?
Because you cannot specify. Okay, this is a global thing. The reset pin is one single wire that is connected to all parts or all important parts of a process. So when this pin, the reset pin, is asserted, meaning it is a 1 in this case, then all components will simultaneously reset to a default state. And without any special specification, the reset condition is always 0. So this register will reset to 0 when that pin is a 1.
What's a 0, 0? 0, 0? What's that?
0, 0. That's the content of the register in hexadecimal. So right now it is specifying 0, 0, 0, 0 in bits, 0, 0, 0, 0 in bits. Because each hexadecimal digit represents 4 individuals. Is that okay? So I think these are all the components that we talked about today, and I just kind of explained it as a component, how do you make use of it. Easier? Okay.
Yeah, I think this one was more succinct and
Well, the other one is in the context of a bigger circuit already. So now you have to kind of plug in these things back into the bigger circuit. So let me see if I can just kind of download and pop up the bigger circuit and see if you have any questions about the bigger circuit at this point. That's the processor. Yeah, last semester I spent about half a semester to actually create the architecture itself, to create a processor. But it was kind of fun because the whole class gets to see how we add different components. So we start with this little simple thing, and then we add the control circuit to glue it, to connect it to something else. So it has its own kind of appeal.
So you spent half of last semester, you said, just constructing it piece by piece?
Yeah. And explaining it along the way. So last semester the explanation is kind of different from how I did it this semester.
Why'd you change?
Because this semester I have it already designed, so I don't have to go through the construction phase to explain it. More or less. More or less. In logic, if you spend enough time to work with it and actually put in all the components, you can actually make a functional processor, but only in simulation. Now there are software out there that can take maybe not the output of logic gates, but it can take the specification of logic gates and how to connect. We call those schematics. Okay, so when you look at the picture, let me show the processor first, then we can just look at that one and refer to it. So want to look at downloads. There we go. Okay, so zoom all the way out. Okay, so when you look at something like this, it is generally speaking called a schematic because it is only showing you logically how the components are connected. This is not how you would wire things up, okay? Because obviously we have a lot of wires that are crisscrossing, which is not possible when you're actually routing something in 2D. But it's called a schematic because we are showing how things are connected, from a logical perspective. So there are software out there that can take the output of this file, which is just an XML file, and convert all the gates to a very low level type of gates, like NAND gates and stuff like that. And you can then take that specification file, load that content into one of two different chips. One type of chip is called CPLD, and the other one is called a FPGA. CPLD stands for Complex Programmable Logic Device. That's CPLD. FPGA stands for Field Programmable Gate Array. Okay, so fancy names, but in the end, what those things are, they are basically programmable actual physical devices that can implement gates. So yes, you can, actually take something like this when it's all done. You can take the whole design, put it onto an actual electronic device, either an FPGA or a CPLD, hook it up to a memory bus, put in some memory into the socket, and actually make it work. And that's actually what people do in the final year project at Berkeley. So if you go to Berkeley and get your computer science and electrical engineering degree, the final year project is to design a processor. Not like this one, it's actually a bit more complicated. It would include all kinds of optimizations and cool stuff like cache and whatnot. But the concept is the same. You're still designing a processor. Not using a diagram anymore, they would use a programming, quote-unquote programming language called a Verilog, which looks like C, and you can use text to specify how things are connected. Right. So,
And just if we do a computer science degree, or is electrical engineering going to go over Verilog, or which one? If you were going to Berkeley and you were doing EE or CS, which one would cover Verilog?
EE. Yep. Yeah, CS will basically stop at the level of a schematic diagram like this. But EE will go all the way to Verilog, which allows you to specify far more complex circuits without all the downfalls of a graphical schematic capture software. Because you can see, if I need to add anything here, it's going to be difficult because I have to move things around and it will just cause all kinds of problems. But when you specify the circuit using text, then you don't have that limitation. And it's a lot easier to make complex design using the text representation. You can check out Verilog, which is Verilog, which comes from verification and logic. Yep, it looks like C. The syntax looks a lot like C, but they use it to specify circuits or gates. Okay, so getting back to what we talked about today, so I will just kind of go over the overview of only this part. Okay, this is basically all we really talked about today. Is only this part here. This is the ALU where all the actual computations happen. In other words, we have the adder and the subtractor inside here. This is the register bank, where you have those 8-bit registers that can store results and also they can supply information for the adder and the subtractor to chew on, to basically to do the process. When you look at each individual component, for instance, if you look at the ALU, which is the arithmetic and logic unit, it looks like this. Okay, so we kind of talked about this today in class. So when you look at the overall diagram, now that we have explained what each individual part is really doing, then it becomes kind of like, oh, okay, so that's what it's doing. Because you can see the input is always connected. This input is always connected to this part of the adder, and the same input is always connected to that part of the subtractor. and the other one connects to the other part of the adder and the subtractor. So the adder and the subtractor do not have any clock signals whatsoever. In other words, they're always interpreting the input and they're always cranking out the output. Okay? Because if you look into what is inside the adder and the subtractor, it's kind of like the 4-bit adder that you have done and the 4-bit subtractor that you do today. Yeah, but inside it's kind of like that one. Okay, so whenever you change the input, the output changes to reflect the
So like it should be like 2 AND gates and the OR gate, and inside those adders and
yeah, a whole bunch of inside. Yeah, and this one does not show you what is inside because it's just seen as a whole unit.
and where are those inputs coming from? The DN1 and the DN0?
Well, this schematic does not show. Okay, so if you want to see
just inputs.
exactly, as far as the ALU is concerned, it only needs to say, okay, we have this interface, and then we have the output. And then we have a way to select, do you want the output of what? Do you want the output of the adder, or do you want the output of the subtractor? And that's the ALU. Okay, you can perform calculations, and you can choose what calculations you want to perform. Now, technically speaking, it is happening all at the same time. You just selected the result of which calculation you want to be presented on the output. Are we doing okay so far with the overall?
And that carry input is all coming in from like a half adder or something like that?
The carry input is coming in from its own quote-unquote register. In other words, the carry output of an add or the borrow output of a subtraction is remembered. The processor has a special place to remember the carry or the borrow of the previous addition or subtraction operation because it is of significance. It is of importance. Is that okay? Any questions about this diagram? Because now that we know what a multiplexer is, now it becomes kind of clear, we use these bits here to specify which input connects to the output. And then we use the output enable bit to specify, do we really want to drive the output? Because sometimes you want to leave the output not driven so that somebody else can drive those particular wires when we look at the overall picture.
What does the C out on that mean?
The out is carry out.
So you're saying, so even so, since it's 9-bit input.
Well, yeah, because the carry and the borrow is a part of the input, so on the output side, I can split it back up into the result and the carry.
And why would we want an outside source to mess with our inputs? Like, so if we decided to disable the output enabler, why would we want to do that? Why would we want other outside sources to come in?
Because, okay, so we have to go back to the main diagram to see that. Okay, so we want to magnify just this part of the circuit. This is the output. This is the carry, which I have not hooked up to anything yet, but this is the actual output. It does not really need a mux anymore because okay. The way it's right now, I really do not need to use an output enable because there's no way it can fight from the other source. Now you can see that this wire and this wire go through a mux, and both of these basically will connect to the input of the register bank. This is the input of the register bank. So that means if you look at how this wire is connected, this one is connected to the memory chip. So that means, in addition to being able to store the result of a calculation, which comes from this wire, I can also use this wire to read the content of a memory location and store that into a register. Is that kind of okay? Okay, let's take a look at this wire here. Okay, let's take a look at this. This is register in, REGIN. And that's the input to the register bank. But when you look at how this wire is connected, it goes to a mux. And a mux has multiple input and one single output. This is the output side of the mux. And what can serve as the input to this mux is going through the memory bus You can see how this one is connected to the data pins of a memory chip, or it can go through, or you can go to the output of the ALU. So that means, the way I can register, the way I can update the content of a register is either to store the result of a calculation, or I can store the content of a memory location. And that is really useful because if I only have the registers connected to the ALU, I still cannot specify where do I get the raw data to process. What am I adding? Well, you can add content to the registers, but how do I specify the initial content of the registers? So I need a way to read from memory and put it into the registers. Does that come in? Okay? That makes sense? Okay. So that's basically what we have today. And then the other part is when you look at, between these two units, the two outputs of the register, which is one is this guy here, and it serves as one of the input into the ALU. The other one is this guy, which is the other input into the register, into the ALU. So this is how we can specify the two inputs into the ALU. So they come from possibly up to two registers.
So the ALU performs the calculation, and then we decide which one we want to spit out. But then we're storing it in the register
Into a register.
But then that's also acting as the input.
Yes.
To the ALU.
Yes.
Okay.
Now,
It's a little circular there.
It is circular in a way, but because of the way we clock it, it will still be okay.
What do you mean? I know what you mean by
Okay,
clock it, but
let's take a look at the register bank here. Okay, so this is the register bank, and it is inside. It looks like this. Okay, we saw this a little bit earlier in class, right? Okay, so we'll go ahead and okay. This won't explain it, but this will. Okay. Remember, in the ALU, we have a way to specify not to drive the output. Like, don't drive the output, don't do anything. And that comes in handy. No, it's the other way. Okay. When you look at the ALU, we have the output enable, we have the data out, so it can reflect the result of a calculation with these pins. And when we go back to the main circuitry, this is the output. It goes through a mux and go to the input of the register bank. And then you look into the registers, the input port of the registers can go to each and every single one of these registers. Now, the trick to do this is not to do the calculation so that you have a circular kind of thing. So when the output or the result of the ALU is inside here, so let's say this is the actual output of the ALU, when we perform changes to these things, we are not going to connect it directly to the output. In other words, we specify register enable 0 and register enable 1 to be zeros. So the registers are really not outputting anything.
So we've done the calculation, we're storing it in two registers, and we're saying don't output what we just stored.
Well, the register outputs will still be the content of each individual register. You still have to hold that output. But once it is updated, okay, I get it. Okay, I know what you're asking. Okay, it has to do with the clock signal.
Okay.
Okay, what does it take for a register to update?
It needs the
right? 0 to 1 on the clock pin, and there's one more thing, which is the enable, right?
yes, declare enable.
Right. Okay. So remember that part. So let's say we set up, this is the result of a calculation, and the registers are already opening here. Okay. So we have the whole circuitry set up. When the enable pin, when the clock pin goes from 0 to 1, how many times is it going from 0 to 1? Once.
Yeah.
right? It's not a sustained signal. It's not like, oh, when it's high, it is always going to update. It's only when it's transitioning from 0 to 1. So at that very moment, whatever is presented here in register in is going to update whatever register you have selected, and the clock goes from 0 to 1. Now, as soon as that happens, as soon as the clock goes from 0 to 1, the content of the register will change, which in return will change the output, which in return will also change the result of the calculation, right? Because those things are all still connected.
Okay.
So these pins will also change at the same time. But why do we care? Because the clock is no longer transitioning.
So since the clock transition, we store the input we have right now, we store because it transitioned from 0 to 1.
Right.
But you're saying when it's transitioning back to 0, and we've already got that.
No. It doesn't even have to. Once it becomes a 1, it's not going to change. Because the signal to change the content of a register is the low to high or 0 to 1 transition, which can only happen once per clock cycle. So after that, yes, once this register is updated, it will go through the mux and change the register output. The register output will in return change the input into the ALU, and then the ALU will change its own output, which means these bits in return will also get changed. But nobody is going to update because the 0 to 1 transition is already over.
And we have to specify on the decoder if we want it to change. So that's why if we were to say register select, I think
Well,
if you can scroll down
right here.
Yeah, so if we were basically saying that the decoder is not going to turn any of those on, then it wouldn't change any of the registers.
But it really has nothing to do with this part. All of these circuits are still static. They are not changing anything. The only one that matters is the clock line, because the low to high transition only happens in an instant. And then after that, we can change the input to the D port. It's not going to do anything anymore.
So what happens to those? Once the clock goes back to 1 again, though, is they going to change it?
Well, the clock, okay, so when we are ready to update to store the result of a calculation, the clock goes from 0 to 1, right?
Stores it.
To store it. And then, we have to, and then during that time, once the clock is a 1, we can do a whole bunch of stuff, including, but not limited to, turning off the decoder, so none of the registers is selected anymore. And then we can put the clock back to 0. We can do all kinds of stuff because nobody is really paying attention anymore. So that we can do all kinds of stuff and not affect the content of the registers.
Now, but if the register enables are both 0 over there on the right, then wouldn't we not be sending anything to the ALU at that point?
It would just be unspecified. The ALU is still getting something, but it's just unspecified.
But is it going to perform a calculation on that something?
Oh yeah, it always does a calculation. It's just, nobody's going to pay attention to the result of the calculation.
So it's kind of like a flap that just keeps going no matter what. We just want to record at what point.
Yep. Because there's no control to disable the ALU. The adder is always active. The subtractor is always active. It's just whatever the input is may not be useful, and the output is nobody pays attention to the output either.
But then we can also disable the ALU output by display.
Yes, you can disable the ALU output, but the input it's the adder. You cannot disable the adder or the subtractor. Those things are always active. They're always interpreting whatever the input is and do the calculation as the output.
And the carry bit is nowhere in this.
The carry bit is not stored in this particular design, so it needs its own little register or latch or whatever you want to call that to remember. And that's why it's not added to the circuit yet. But the circuit as it is right now, which is the main part here, does have all the major components. It has the ALU to do the calculation, it has the register to store the intermediate results, and everything is still connected to the RAM, so they can store the result of an addition from a register back into RAM. So this way, if you want to traverse an array and add up all the values of an array, you can actually do it. The pathways are there to add the values from multiple locations of memory and take the sum and put it back into memory. Now, we haven't really talked about the glue logic to connecting your RAM to the registers, because we want to be able to read the content of a memory location and store it into a register, and we want to do the opposite as well, take the content or the value of a register and store that into memory. Now, that we have not talked about yet. That's something that we'll talk about next Tuesday. And then once we talk about that mechanism, then we'll start to talk about the control mechanism, which is the microcode mechanism. So the microcode mechanism is the one that is kind of like it's basically really just like a music box. You know how in the music box you have all those pegs, and when you wind it up and you let it go, it will just kind of slowly rotate the drum, and then the pegs will play the individual pieces and make the music. It's the same thing here, except you're looking at individual bits to turn on the output enable here and clock here, turn off the output enable here, turn on the output enable over there. So it's like the conductor. And what we have now is the individual music instrument. So we need a conductor to basically give the signal to each piece and say, okay, I want you to do this now, and I want you to do that now. Okay, now both of you keep quiet, and I want you to do something. So that's the one that is orchestrating everything, so that the processor will function as a whole to do what it has to do. That okay? So we have a coordinator, and the coordination is not, we have not talked about that. So at this point, we're still focusing on the individual part. Like today, we talked about the register bank, we talked about the ALU. So those two are kind of like, oh, here's a violin, and here's a flute. So now we understand, how to play a violin, we know how to play a flute, but we don't know when to play a violin and when to play the flute, and what note to play. So it's up to the conductor to kind of coordinate, that part. And we haven't really talked about that part. And this took me like 3 weeks, just to get through the material of today's class. That took me about 2 to 3 weeks to get this processor basically done. And before last semester, I did not even know about logic cisp. It's after the semester had started, then I found out, hey, it's logic cisp. I can teach this class using this tool. So during the semester, I just started to integrate logic cisp into the class. So that's why you guys are kind of lucky, because all that work is done. But you guys are kind of unlucky because you took 360 from me, and that's the first semester I taught that 360. And I talked to Dave Fox today, and he said, really, your students don't know how to write subroutines, because we didn't really have a lot of time to write subroutines. But you guys actually wrote one, there's one homework assignment that has a subroutine, but that was it. And that's because I spent too much time to talk about debugging in the class. You guys remember how much time I spent on the debug, not the debug, but the error checking logic, checking whether you're reading a number or not, and how to clear in so that you can read the next number. You can read character, you can clear character by character until the error condition clears. So we spent a lot of time to talk about how to debug programs, how to do error checking and stuff like that. So we ended up not having enough time to talk about subroutines, parameters, and stuff like that. We did. I talked about it. I gave you guys examples. We went through a lot of recursive examples in that class. But in the end, you guys did not have enough time to practice and write code using subroutines.
Yeah, my one recommendation would just be a few more homework assignments for your 360.
Yep.
I mean, that would be my only.
Yeah, but that's why I'm changing the structure of 360 this semester. So in the lecture, I'm not going to talk about debugging. All the hands-on stuff, I don't talk about it during the lecture, and I move all that stuff into the lab time. Because this time, I specifically requested David to schedule
360 with full face-to-face lab and full face-to-face lecture. So I have like twice the amount of time to talk about stuff. You can watch the videos from this semester. Yep. And we are already starting to talk about subroutines. I've rescheduled the topic a little bit. So I'm starting to talk about subroutines right after expression, not even to wait until we talk about control structure.
Yeah, I may want to watch those videos because I learned a lot last semester, but it definitely felt like it was your first semester teaching it. But I learned a lot, but at the same time I was kind of a little unsure on some things.
It's the sequencing of the topic, that makes it kind of, that's the tricky part. All of that stuff is here. It is just, how do I sequence the topics? And with assembly, I have the whole thing down already. So, so this is not going to be a problem with this class. Right. Any other questions? The recorder is still going.
I was going to ask, did you go over the RAM chip real quick and just make a review of that?
Yeah, we can do a quick review. Okay, the RAM chip, which is here, has the address bus, which specifies which location we are looking at. Look at this as the index of an array. Okay, so this is the stuff inside the square bracket of an array. Select is kind of like, when you have multiple RAM chips, this is useful, but since we only have one, it's not nearly as useful. Okay? Because if you have multiple RAM chips, all of the A pins will be bundled. Okay? In other words, when the process says, when the processor says, I want location 23, all memory chips will hear that the processor wants location 23. Okay? But we really only want one of the memory chips to give me its own location 23. So that's why the select pin is useful, because there's one select pin connected to the processor, and they're all distinct. So if you have 4 RAM chips, each one of the RAM chips has its own select pin, and the processor has a different pin that connects to each select pin.
And it's just a single bit, 1 or 2.
Has a single bit. Yep, and you can kind of tell because it's blue in color. Well, I guess it's not obvious here. Yeah, it's still not obvious. But it's basically one single pin. This is the clock, and the clock is useful because when you go from 0 to 1, you can update the location in RAM. Kind of like a register. A register is kind of like a single byte every module. Load is controlling whether we are reading or writing. So from that perspective, it is different from a register, because the Q part of a register is always screaming. It's always telling everybody, or wants to tell everybody, the content of the register. With a memory chip, it's not the same. If the load pin is a 1, it means we are loading, which means we are reading from memory.
From the address port.
From the location specified by the address port. Okay. So when a chip is selected, this is the 1, then whatever you specify in the address bus will control which location is addressed. The content of that location will then be presented onto the data port.
And the clock also has to be true.
No, the clock has nothing to do with reading. It only has to do with writing. The clock is not used when you are reading from memory. It is only used when you're writing from memory.
So that means when we're sending something out, what do you mean writing?
Writing is from the perspective of the processor. So when the processor is trying to update a location in RAM, the clock signal is used. But when, on the other hand, when the processor is trying to read the content of a location of memory, the clock line is not used. Okay. The clear line is the same thing as a reset. Basically, when that pin is asserted, or when it becomes a 1, all content of this RAM chip will return to 0. All simultaneous. So it's basically a hardware way to zero out memory content, so you don't have to rely on software to do it.
What is 000408 That's all.
That's locations. Yep. So it basically means this is location 00, location 01, 02, 03, location 04, 05, 06, 07, and so on. It will just reflect the content. I can't really easily do it here because everything is already tied in, so I can't really run just the memory chip all by itself here.
Okay.
So basically what you do is you specify the location of where you want to store using the address bus.
We're indexing an address of an array.
Right.
And
So
then-
this is the index. This is what goes into the square bracket of an array.
Okay.
This specifies the content of that memory of that array element.
But that's only that's only an output though, right?
It can serve both purposes.
Okay.
The data port can serve both purposes. In other words, it depends on whether your array element is on the left-hand side or the right-hand side of the equal symbol. If the array element is on the right-hand side, it is a read operation. In a read operation, the data bus is driven by the memory chip. The memory chip is now saying, hey, if the content of this location is da 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 da, and hopefully the processor is paying attention so it can read that content, right? On the other hand, when you're doing a write operation, it is kind of like having an array element specified on the left-hand side of the equal in C and C++, because you're updating the memory location. So in that case, you have to first specify which location or which memory content or which location in memory they are trying to overwrite, to specify the new content of that location. Okay, so you have so the processor now has to drive not only the address bus but also the data bus, and then it will put a 0 to the load line because load is 1, store is 0. Store is from the perspective of the RAM chip. You're storing the content. You're overwriting the content of a location. So you would specify a 0 to LD load. You would then assert select to mean, yes, you, memory chip number blah blah blah, I'm talking to you. And then you will clock the clock line. So when the clock line goes from 0 to 1, at that moment of the transition, whatever you specify on the data bus is going to overwrite the location in the memory chip, and the location is now specified by the address. But only at that instant, when it transitions from 0 to 1. And then after that, the write operation is all done. So normally what the processor will do is to take the clock line back to 0, deselect the chip, and as soon as you deselect the chip, you can the data bus is free to do other stuff.
And all those zeros are location, right?
They are content at those locations.
Okay.
So if you right-click on a memory chip of a RAM chip, you can go to Edit Content, and now you can use your, basically it's a hex editor. You can enter the bit pattern of each location in hexadecimal.
That makes more sense. That was confusing me seeing it that way. But
Yeah, that's just a small window of the actual content of this memory chip. Because the address bus is an 8-bit address bus, which means we have up to 256 locations in the memory chip, and it's only displaying like the first bunch. Now, in fact, if you specify anything on the address bus, you will see this will scroll. It will always kind of show you the one. It will always make sure that the one that is actually selected by the address bus is within this window. So it really is just kind of showing you what is happening right now. But it's a smaller window compared to the full memory content of that chip.
And those are going to be split in hexadecimal. Well, that would be in the regular bit pattern.
No, that's in hexadecimal as well. Because when you look at each byte location, it is specified by 2 digits. So they have to be hexadecimal digits. Because you have, each row has 16, and there are 16 rows. So 16 by 16 is 256. So that specifies the full content of a memory chip where the address bus is 8-bit wide. Because when the address bus is 8-bit wide, then you have 2 to the power of 8, which is 256 locations. And that's exactly the number of locations in the hex editor. Well, I mean, the other one is, if it is called a hex editor, it means, it is a hexadecimal editor. So content in memory is specified in hexadecimal. Any questions? still being recorded.
No, and I'll probably look over that. I guess for whatever reason, Joe, what you said makes perfect sense. But for whatever reason, my brain is like.
Because it's late and your blood sugar is running low.
No, but no, it makes sense.
Yeah, the other guy had to drive back to Yuba City, so it's a 2-hour drive from here. So I was half joking with him and saying, do you want the audio part of the class recording because you can listen to it again on the drive? Before you get home, you would have reviewed the whole class already.
Yeah, there was a nickname my friend had for Yuba City that because it's so destitute, they call it. Well, I don't want to say it, but it's called Yuba Shitty. So.
Yeah, Yuba City used to be where they transport trash from San Francisco. Now it is Livermore. Yes, trash from San Francisco gets trucked all the way to Yuba City, and now it's trucked all the way to Livermore.
Well, Livermore is closer to.
It is closer, but we are running out of landfill.
Well, yeah, they're having that problem in like Rockland or Roseville where the landfill is starting to let out a really foul stench in all the neighborhoods.
Well, they always do, but if you think about it, when you take out trash every week, you're going to have to think, where is it going? And if you think about it, every week you have one, let's say 32 gallons of container full of, trash. 1 year you have 52 of those things. So 52 times 30 is 1,500 gallons already. And they have to go somewhere, and that's from one household, and it's a small trash can, because a standard size trash can is 64 gallons, not 32. 32 is the kind of like the small, tiny little ones. So you double that to 3,000 gallons per household per year. And it has to go somewhere, and this is not stuff that is just recycled or reused or, blah, 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 blah. It is filling up, some place in a landfill. Incineration can be done, but it also creates problems because when you incinerate trash, regardless of the content, it will release dioxin, which is a very toxic, substance. It has been shown that people who live close to fossil fuel generator, for electricity, there's a much higher mortality rate because of the release of dioxin. So that's why they don't want to incinerate either, because it generates all this dioxin. So the best way to do it is to what they call diversion. So instead of putting everything into the trash can, now they separate. The first one to get separated out will be stuff that is worth money, like your aluminum cans, glass, stuff, plastic stuff. So they go into the recycle, and hopefully, people do a good job at recycling and have that part handled. But the other part that is starting to happen in Sacramento, but not in full force yet, is compostable stuff. Yep, but it takes a lot of time to educate people because people keep throwing the wrong stuff into the wrong part. But if it is done right, the compostables, would really help because that's basically a paper plate. All the leftover food, even if it's spoiled and, growing mold and whatnot, it doesn't matter because they put those things into a huge commercial composter. And they put bacteria, to ferment and, make use of that stuff. So in the end, they come up with, the outcome of all this is, stuff that is actually usable with no or very little, toxic, byproducts. So it's called diversion, which means, you're separating, what used to go into trash in one single can into different things, and you're diverting things that can be reused away from landfill. So we'll still be using landfill, but hopefully we'll be using those, less and less, so it will take longer to fill up all the landfills.
Yeah, we're having a problem with the garbage patches in the ocean now.
Garbage, it's an island, right?
Yeah, it's just basically a gigantic island of trash. So just one garbage patch in the Pacific Ocean, and this is the conservative estimate, is about the size of